Hi, thank you for tuning in. My name is Benjamin Tesler, and I am a PhD candidate in the Biomedical Engineering program at SUNY Downstate. My advisors are Steve Fox and Jeff Goodman, and I'll be showing you my presentation titled Comparing the Focality Across Non-Invasive Brain Stimulation Techniques. The first thing to understand is what is it that influences neurons in the brain? When we set up a voltage difference with electrodes across some distance, we create electric fields, which, when multiplied by the conductivity of the medium we are stimulating over, we drive charged particles through the medium and through the neurons. Something important to note is the resulting influence of the electric field on the neuron depends on the direction of the electric field relative to the neuron's branches, such as the thickest branch, the apical dendrite. As can be seen in the right figure, if the electric field is flipped, so does its relative membrane polarization, which would be directly related to its effect on firing rate. However, our electric field equation that was from the previous slide holds only for a uniform electric field, which would only be in effect when we inject current across the entire cross-section of the media. As can be seen on the left, we set our current injection on the leftmost face and our return current on the rightmost face of our block we are stimulating. On the right, we reduce the size of the electrode to show how the electric field is strong by the electrode but quickly drops off in all directions. Therefore, if this block was filled with neurons, we would only be stimulating the neurons close to the electrodes. The challenge in non-invasive brain stimulation is how can we target a specific region of neurons without affecting undesired neurons? And an even bigger challenge, how can we target neurons that are deep all while keeping our stimulators outside the brain? The three main methods of non-invasive brain stimulation that I'll be discussing here, two of which are transcranial electrical stimulation, one being the conventional approach with sponge pads or high definition montages, and temporal interference stimulation, and the third being transcranial magnetic stimulation. The conventional method uses square sponge electrodes to inject current across the head from an injecting current electrode lead and a return current electrode lead, which would have equal but opposite strengths at the electrode surface, while the high definition approach uses much smaller electrodes and multiple electrodes for the return current electrodes, so that the return currents are more diffused and are effectively reduced. There are over 10,000 publications in the field and growing due to its ease of use, safety, and cost. Also, because electric fields influence the most elemental property of the brain, we can possibly treat almost any brain related disease or illness. Temporal interference takes a different approach. We use two pairs of electrodes, each injecting its own current applied at a specific frequency. Pair 1 is at frequency F, pair 2 at frequency F plus delta F. For example, F1 would be 2000 Hz and F2 2005 Hz. At the midline down into the brain between the two closest electrodes, we would see the envelope of the electric field with an interference pattern at the frequency difference, which in our example will be 5 Hz. This is otherwise known as a beat frequency or an amplitude modulated wave. The assumption is that the neurons are influenced by the beat but not the higher carrier frequencies. Thus, we can possibly get more specific and target deep structures with our stimulation compared to conventional approaches. This method has been a hot topic and is only recently gaining momentum with 500 publications. It's only twice the cost because of multiple stimulators necessary and has the potential to treat the same things the conventional methods can, but with perhaps more precision. Transcranial magnetic stimulation uses superconducting coils that sends current in a circle, which according to Maxwell's electromagnetic equations creates magnetic fields through the air, which in turn creates current deep in the brain, otherwise known as eddy currents. This has over 100,000 publications, has been FDA approved for migraines, depression, and OCD, but has a price tag of $50,000. To get a better intuition for temporal interference, I've put up two examples of two temporally interfering waves. This is the resultant wave of the summation of two frequencies, the top with equal intensities and the bottom with unequal. The envelope amplitude is double the minimum of the two. Because of the difficulty of showing electric fields in three dimensions, I am showing three cross sections in three different planes, the YZ plane, the XZ plane, and the XY plane. Each progressing image is when the distance from each injecting electrode to the midline gets larger. The first row is the peak electric field from the blue electrode pair, and the second row is the peak electric field from the red pair, seen at the top figure. The bottom row is the beat frequency amplitude, which is 2 times the minimum between the two. As can be seen, as the midline distance gets larger, the electric fields can penetrate further into the medium. Also, something to note is when the distance gets large enough, the maximum electric field of the beat frequency gets smaller and smaller, as seen in the axis of the color bar to the bottom right, outlined in red. Therefore, if one needs a certain level of intensity to activate neurons deep in the tissues, one may need to raise the intensity of the original current injection to an unreasonable level. A limitation for the magnetic stimulation is that the electric fields that are created are only in the direction parallel to the medium surface, as can be seen by the arrows in the left figure. This would mean that the neurons that are effectively stimulated would be the ones with their apical dendrites pointed in that direction, on the wall of the sulcus, as can be seen in the figure to the right. A limitation to the conventional electrical method is that the current is not injected uniformly on the electrode surface. There is an annularity that occurs because of the electrode's higher conductivity relative to the medium's conductivity. As can be seen for the three different electrode conductivities used, the electric field has a peak close to the edge of the electrode, which gets larger relative to the electric field at the center point as the electric conductivity increases. Here we compare three planes from the three methods that we have been describing so far. We are using a ring for a return current electrode for the conventional approach in order to make the electric fields completely symmetrical. As can be seen, the conventional's electric fields do not go very deep compared to the temporal interference and magnetic. To study this further, I analyzed electric fields for many different size electrodes for each technique. Each black bar inset is one of the parameters that I iteratively changed and then simulated its electric field. For the conventional case, I changed the radius of the injecting current electrode, the separation distance of the injecting and return current electrode, and the thickness of the return current electrode. For the temporal interference method, for both pairs of electrodes, I changed the distance between the injecting current electrode and the midline. I changed the length and width of the injecting current electrode, and I changed the separation between the injecting current electrode and the return current electrode. For the magnetic stimulation case, I changed the radius of the coil, the separation of the two coils, and the thickness of each coil. To measure how changing each of these parameters changes the electric field, I calculated the distance from the surface to the point at which the electric field is equal to half of its maximum, called d half. I also calculated the volume of which the electric field is greater than half of the maximum, called v half. Then I calculated spread, which is v half divided by d half. In the top figure, I show electric fields using 15 colors, illustrating what are the 3D surfaces where the electric fields are equal. And in the bottom, I show only two colors where they are separated at the half maximum. Thus, V half would be the red volume, and D half is the length of the yellow arrow. Therefore, if we want a non-invasive brain stimulation technique that is precise at targeting deep, we want one that has a small spread and a large D half. Here I show a comparison between the three methods, and within each of the three methods, I am showing what's changed when iterating over the various parameters that was described 2 slides back. Each point on the scatter plots is a simulation with the y-axis being spread and the x-axis being d half. Therefore, we want the points to be as far down and right as possible. The top row of plots is the temporal interference approach, the middle row is the high definition conventional approach, and the bottom row is the magnetic approach. The plots on each row are the same except for the colors, which is set to be one of the changing parameters for each method. For the temporal interference case, in the top left scatter plot, we can see a robust change from red to blue from the axis origin to the top right of the graph. The red is when the midline distance is 2 millimeters and gets larger as the points get more and more blue. From looking at the next three plots, the length, width, and electrode separation does not seem to do as much. Thus, it seems the midline distance is the most important parameter to control for when doing temporal interference stimulation. The right plot of the top row shows that as we get a larger midline distance and d half, we trade off the maximum amplitude of the beat frequency relative to the maximum intensity of the single frequency current injection. For the conventional high definition approach, constricting ourselves to the 0.08 Siemens per meter electrodes to reduce annularity effects, the parameter that changes our electric fields the most is the radius of the injecting current electrode. This can be seen at the leftmost plot on the middle row, with the colors going from red to blue from the origin to the top right of the graph, indicating the radius growing from 1 to 11 millimeters. And for the magnetic approach, the parameter that changes our electric fields the most is the radius of the coil, as can be seen in the bottom left plot. As can be seen in the bottom right scatter plot comparing all three methods, the conventional approach in green does much worse compared to the other two techniques. The temporal interference and the magnetic stimulation approach seems to be comparable until the D half gets large enough. Then it seems the temporal interference outperforms the magnetic stimulation. Therefore, we conclude that for our measurements we are analyzing, temporal interference seems to be a much more precise method of the two electrical stimulation techniques, which should give much better efficacy in the clinic and in research. It seems that it can do just as well as transcranial magnetic stimulation, but at a fraction of the cost, which is important for labs, startups, and clinics in areas without many resources. Thank you for your attention. Please email me questions at benjamintesler@downstate.edu.